Let's motivate the idea of improper integrals by talking about probability again. So our main topic is improper integrals, but we're putting it in the context of probability. We've talked about normal distributions. Let me talk about another kind of important distribution called an exponential distribution. Exponential distribution. What is its PDF? Probability density function. Little f. I'm going to call the variable t instead of x. Why? Because one of the most common applications of exponential distributions is the situations where you're modeling an amount of time. For example, I'm going to say this example even though it's a natural disaster because it's an important example, earthquakes. We just had an earthquake. You live in Southern California. You just had an earthquake. How long will it be until the next big earthquake? I'm not talking small earthquakes. I'm not talking aftershocks. I mean the next big earthquake where we have to wait 1 year, 2 years, 3 years, or more, 100 years. Very important to me, actually, because my youngest daughter lives in Southern California, in fact, close to the San Andreas Fault. So I'm praying she's safe. Actually, she's on her way home in a plane right now as we speak, because it's her wedding shower. She's getting married soon this weekend. Anyway, coming back to the situation, what is an exponential distribution? It's got a PDF that is an exponential decay function. Allowing for some unspecified constants, a common letter used for the unspecified constant here is the Greek letter lambda. Lambda e to the negative lambda t power. Lambda is a positive constant. The value that this constant lambda takes depends on the situation. Are we modeling earthquakes in California or are we modeling earthquakes in Minnesota? We do get earthquakes in Minnesota. They are usually not felt because they're so small. We could try to model big earthquakes in Minnesota. It'd be a very long time until the next earthquake. But in California, not so long. The value of lambda depends on the situation. T is time in the application, and it would be positive. I'm going to write it as greater than or equal to 0, though you could, well, okay. You could write it as strictly greater than 0 or greater than or equal to 0. It doesn't really matter. I'll put greater than or equal to 0. What do we want our probability density functions, our PDFs, to do? We want to be able to integrate them to calculate probabilities. The probability of the time until the next earthquake, call it capital T, being between two numbers, A and B, is supposed to be the integral of the PDF over the interval from A to B. With normal distributions, we did this kind of thing as well. And we also talked about how integrating the normal distribution has to be done numerically because, well, it can't really be done symbolically without invoking the error function. So you either you have to use technology in some way is the point. Some technology that can compute values of the error function, or do, for example, Simpson's rule to calculate areas under normal curves. But for this example, it turns out you can find an antiderivative of this pretty simply, though we will not do that today. That's not our main purpose. To calculate this interval, you want the probability over all possible values of t, your so-called random variable, to equal 1 to be a valid probability density function. You want the integral to be 1 over all values of t. What are all values of t for this example up here? All values of t greater than or equal to 0. So we want to choose lambda effectively, or maybe the value of lambda doesn't matter. We want 1 to equal all the probability, so to speak. In our case, that's the probability that t is greater than or equal to 0, that the next earthquake happens sometime in the future. Could be 1 year, could be 2 years, could be 50 years, could be 100 years, could be 1,000 years, could be 1,000,000 years. It's going to happen sometime. We want it to be a sure thing. As a practical matter, it is a sure thing. What's the integral over all values of t? In this context, I'll go ahead and put our PDF in here. It's the integral from 0 to what? Infinity? Yes, we write integral from 0 to infinity. But when we write this, we need to realize this is not an ordinary kind of integral. We don't typically have infinities as limits of integration. Here we are. Because it's not an ordinary proper integral, we call it an improper integral. How is it calculated? Using a limit. Limits never go away in calculus completely. They are the basis of everything in calculus. I mean everything. It's what makes calculus calculus. Though in practice, right, there's all these tricks that allow us to avoid limits. Product rule, quotient rule, chain rule for derivatives, fundamental theorem of calculus for integrals. Maybe there would be some tricks here too, but that's not our point today. By definition, this is the limit as the upper limit of the integral goes to infinity of a bunch of ordinary proper integrals. Assuming that limit exists. Maybe it doesn't exist. If it does exist, listen really carefully. If it does exist, we say the improper integral converges. If it does not exist, we say the improper integral diverges. Very important words. If the limit exists, we say the integral converges. If the limit does not exist, we say it diverges. We just need to keep going here. Try to calculate this limit. Carried along for the ride. Always have it there until the very end. Okay, I'm going to be looking for that until the graders to look for that. I want the limit signs to be there until the very end. Can we do this with the fundamental theorem of calculus? Yes, a little bit of guessing reveals that negative e to the negative lambda t is an antiderivative of lambda e to the negative lambda t. Just differentiate that in your head to check it. The chain rule would give you an extra factor of negative lambda. The negative signs would cancel, and you'd get the function you're integrating. If you can't guess that in your head so easily, w equals lambda t works, or negative lambda t, to help you figure this out. Plug in the numbers for t. Plug in t equals b. Subtract what you get when you plug in t equals 0. Either the 0 is 1, 2 minus signs make a plus sign, and you're left with the limit as b goes to infinity of 1 minus e to the negative lambda b. Does this limit exist as b goes to infinity? It depends. Depends on what lambda is. If lambda is positive, like ours is, then negative lambda is negative. B is going to infinity, so it's positive. Negative times a positive is negative. We're getting larger and larger negative exponents, like negative 100, negative 1,000,000, negative a Google. E to such numbers gets really, really small. It goes to 0. Now at the end, you can replace that with 0. And the final answer is 1. This is since lambda is positive, so negative lambda is negative. And yes, we got 1. We wanted it to equal 1. And we got 1. It worked as long as lambda is positive. And it doesn't matter what lambda is, as long as it's positive. What's going on here geometrically? The graph of our PDF is an exponential decay. F of t equals lambda e to the negative lambda t, exponential decay. It never touches the axis. It's got the t-axis as a horizontal asymptote, though it is exponential decay, so it is approaching it pretty rapidly. We've just said the integral from 0 to infinity is 1. The area under this curve, as the curve goes out forever, is finite. How can that be? How can this area that goes out forever past the edge of the universe, seriously, how can that possibly be finite? It is, because this limit is finite. That's why. Of course, you can't literally get out some tools to try to measure the area of a region that goes out forever and ever, because you can't go out there forever and ever. So this is more of a definition that makes mathematical sense. It does end up making practical sense in a lot of circumstances too. The limit does exist and it does equal 1. So we're happy. This does satisfy the conditions a probability density function needs to satisfy. Applications of these things are huge. Statistics used all the time in business, including exponential models like this, for example, for earthquakes. You want to know what exponential model is good if you're an insurance company, for example. Actuaries use these models all the time. They do modeling work for insurance companies. Another important class of examples is called a power distribution. Power distribution, where the PDF, I'm going to call the variable x this time, f of x is some constant c divided by x to some power p. The domain of this is not all positive values of x. It's one of two possibilities. Either x is bigger than 1 or between 0 and 1. Actually, there's more possibilities. You could consider situations where x is bigger than 2 or bigger than 3, for example. C and P are positive constants. And x, there's two cases. Case 1, x is bigger than 1. Case 2, x is between 0 and 1. You would not want to do both cases at the same time. They're not modeling the same thing. In case 1, it's modeling values of a random variable that are always bigger than 1. In case 2, it's modeling values of a random variable that are always between 0 and 1. Case 1 is a more common kind of model, but you could consider case 2 models as well. Let's consider case 1. We once again want this to be a probability density function. We want the integral of this function over all values of x in the domain to equal 1. Does it? It should seem like probably not. I mean, c and p are arbitrary. How could this integral possibly equal 1 no matter what? And if you thought that, you're right. It doesn't always equal 1. We're more concerned at the moment is, does it converge or not? Does this improper integral's limit definition exist or not? It's a limit of proper integrals, and I'm going to write the integrand function, the PDF, in this way because that'll make it a little easier to integrate. Looks like we need the power rule for integration, right? Where you add 1 to the exponent and divide by the same number because it's a power function. Though the case where p is 1 is tricky because that involves a logarithm. So we really have subcases here. Subcase 1, p. Okay, well, is this p1 or not is one way to write the subcases, but it's going to be better to do, is p bigger than 1? Subcase 2, is p less than 1, and also I'm assuming p is positive. And subcase 3, p equals 1. That'll be a special case because the integral will involve a logarithm in that case. All right, let's consider subcases 1 and 3, 1 and 2, excuse me. Ignore that. Let's pretend p is not 1. Then I can do that integral by adding 1 to the exponent and dividing by that same number, which can also be written as, instead of negative p plus 1, it can be written as 1 minus p. X is going from 1 to b. Lots of letters here. Keep track of what's what. That's the limit as b goes to infinity of cb to the, maybe I should write the exponent there as 1 minus p as well. 1 minus p over 1 minus p minus 1 to any power is 1. So we get this. Question is, does this limit exist or not? The answer is, once again, it depends. It doesn't depend on c for this limit to exist. It depends on p. Subcase 1, if p is bigger than 1, in that subcase, that's equivalent to saying p minus 1 is positive, which is equivalent to saying 1 minus p is negative. That's a negative exponent for the b if p is bigger than 1. Like, it's like b to the negative 1 or negative 2 or negative 2.7 or something. B to a negative exponent does go to 0 as b goes to infinity. Why? This can also be written as c over 1 minus p, b to the p minus 1, no matter what p is. And if p is bigger than 1, that's a positive exponent of the b in the denominator here. As b goes to infinity, that'll go to infinity. C over something going to infinity goes to 0. This limit will exist and be 0 minus c over 1 minus p if p is bigger than 1. That simplifies to c over p minus 1. Effectively, I just brought the minus sign down into the denominator, which is a positive number in this case, as it should be if it's going to represent probabilities. If p is less than 1, if it's between 0 and 1, in that case, p minus 1 is negative, so 1 minus p is positive. I've got b to a positive number here, which goes to infinity as b goes to infinity. If it were a b squared or a b cubed or a b to the 4th or a b to the 2.7, b even to the 0.1 power is going to go to infinity. It's infinity if p is between 0 and 1. Now, in writing this, I'm not saying infinity is a number. It's just shorthand notation to say the integral diverges when p is between 0 and 1. If p equals 1, then this integral is really the integral of c over x. You get the limit as b goes to infinity. What's the integral of c over x? It's c times the natural log of the absolute value of x. In that case, and when you plug in x equals b, you get c times the natural log of b, and actually no absolute value signs are necessary there. You know from Calc 1 or even from pre-calc that logarithms go to infinity as the input goes to infinity, though very slowly. This is infinity. So the upshot of all this is that this improper integral converges to a finite number if p is bigger than 1 and diverges To infinity, you might say if p is between 0 and 1, including if p equals 1. And this integral is worth remembering for the rest of this class. In fact, many people do remember it, sometimes to their dying day. Okay, it's a very famous result in calculus. We've got 3 minutes. What about case 2? What was case 2? X is between 0 and 1. Then I'd want the integral of this from 0 to 1 to be 1, possibly, or at least to exist. That doesn't look like an improper integral. But guess what? It is. Because this function here has a vertical asymptote at x equals 0. Infinite extent region that we're trying to find the area of. Is it a finite area or not? Answer is it depends on what p is. It's a limit as the lower limit of integration, call it a, goes to 0 technically from the right. We don't have time to do this calculation. What you end up getting is that this integral right here converges if p is strictly between 0 and 1, and diverges if p is greater than or equal to 1. Notice these two things are almost opposites of each other. The first case converges when p is bigger than 1 and diverges otherwise. The second case converges when p is less than 1 and diverges if it's greater than or equal to 1. In both cases, if p is 1, it diverges, because in both cases, if p is 1, you get the natural log. Goes to infinity as x goes to infinity, goes to minus infinity as x goes to 0 from the right. Vertical asymptote at x equals 0 for ln of x. Have a good day.